In this video, we're going to talk about a topic called goodness of fit. And goodness of fit is basically measuring how well observed data corresponds to assumed data. So the first thing I would like you to print out, it's called chi-squared testing. Sorry, chi-squared testing. One thing I want to make sure that you print out is the chi-squared distribution table. So really similar to the standard normal distribution table and the student t distribution table that we used for proportions and for means. We want to make sure you have a copy of the chi-squared distribution table as we go through all of these problems. And one quick thing to point out, the chi-squared distribution table is not a normal distribution. If you look at that graph at the top, it's skewed a little bit to one side. Chi is the Greek letter chi that you see there. It looks like a script like X. And we're always calculating in these problems right-tailed tests. So the critical region is always going to be the area to the right of the chi-squared value. So again, just like the student t distribution, we have degrees of freedom on the far left-hand column. And then the chi-squared areas along the top, the shaded area, it says for alpha, chi-squared is the subscript. So 0.995 is first and 0.990 and so on, all the way to the far right, 0.005. The one that we're going to be interested in most of the time, unless they tell us otherwise, is a significance level of 0.05. So this column right here, about 3/4 of the way over. And then the degrees of freedom are given on the left, and the chi-squared values are given in the table. Okay, let's get started. Let's say a survey of 40 randomly selected men and 40 women collected weights. By analyzing the last digit of those weights, researchers can verify whether the weights were obtained through actual measurements or having the subject self-reporting. So just looking at the very last digit. Given the following frequency distribution of the last digits, test the claim that the sample is from a population of weights where the last digits do not occur with the same frequency. This would suggest that people are reporting their weights and they're not being measured. If the weights are being measured, we would expect all of the possible last digits to occur with the same probability. So here's our frequency distribution. If the last digit was 0, that happened 7 times. If the last digit was 1 pound, that happened 14 times. And if the last digit was 2 pounds, that happened 6 times, and so on. So we're going to decide whether or not these reported weights came from actual measurements or having them reported. Okay, so remember, our claim was that the population of weights from the last digits do not occur with the same frequency. So in other words, people reported their weights. So here's what that looks like with our claim. The original claim is that the digits do not occur with the same frequency. So at least one of the probabilities, the probability that 0 is the last digit, the probability that 1 is the last digit, and so on until the probability that 9 is the last digit, one of those probabilities is different, is bigger or smaller than the others. The opposite of that claim is that all the probabilities are equal. Every single last digit of the weight has the same probability of occurring. Okay, that will be our null hypothesis because it's the one that contains the equal signs. And the alternative hypothesis, we're just going to say at least one value is not equal. It could be 2 or more, but at least one value is not equal. A quick example of this, if somebody asked, let's say my dog's weight. If somebody asked my dog's weight, I probably wouldn't be as specific as 53.7 pounds or 54 pounds. I might just say 55 pounds or 50 pounds. So some of the digits sometimes appear more frequently than others if you're self-reporting. If I take my dog to the vet and they're actually being measured, you're going to get a more precise last digit, and each last digit would have an equal chance of showing up. Okay, let me show you how to do this. So First of all, use the chi-squared test statistic, which has its own formula. The formula is a little complicated, so when we do these problems, I'm going to show you lots of steps. Here's the formula. Chi-squared, our test statistic, is the sum of the fraction O minus E, where O is the observed frequency and E is the expected frequency, divided by E, the expected frequency. Squared, and then divided by E, the expected frequency. So again, O is what we call the observed frequency. E is what we call the expected frequency. The O's, by the way, are what we have listed right there. 7, 14, 6, 10, 8. Those are our observed frequencies, and E is our expected frequency. Okay, so here's our frequency distribution again. Let me show you how to calculate the expected frequencies. Now remember, we would assume that each last digit of their weight has an equal chance of showing up. So first of all, add up all of your observed frequencies, 7 plus 14 plus 6 plus 10 plus 8 plus 4 plus 9 plus 6 plus 12 plus 8, and you'll get 80. So N, the total number of observed weights, is 80. We calculate the expected frequencies using the following formula. N, the total number of weights, times P, the probability that whichever one we're looking at, the probability, let's say, that the first one will appear. So for the first case, there are 80 weights, and each probability, each last digit should have the same chance of being observed. So 1 out of 10. There are 10 possible last digits from 0 to 9. So 80 times 1/10 gives us 8. When we go to the next digit, though, the last digit being 1, it has the same probability, 1/10, and we're multiplying it by the same total, 80. So we're going to get 80 times 1/10 is 8 again. Actually, all of these should have 8 for the expected frequency because each last digit should have the same probability of showing up in the data. So while our observed frequencies are all over the place, the expected frequencies for each of them are 8. Okay, O minus E. Remember, that was in the numerator of our problem. So O minus E for each one of these. In the first, it'll be 7 minus 8, which is -1. In the second one, 14 minus 8, which is 6. 6 minus 8 is -2, and so on. 10 minus 8 is 2. 8 minus 8 is 0. 4 minus 8 is, -4 and -3. A comment on this, since our O minus E is being squared, it doesn't matter after we square these whether our O minus E is positive or negative. We'll square it and we'll always get positive results. Before we jump into more calculation, a quick note on what this is doing. This is calculating the difference between what was observed and what we expected to happen. So we observed 7 weights with a last digit of 0, but we expected 8. We observed 14 weights with a last digit of 1, but we expected 8. So how far off was the data collected than what we expected? Okay, so that's what the O minus E column is. And then we square each one of those values to get O minus E squared. Okay, what we're going to do is we're going to divide each of those O minus E's by E by 8. So adding another column, dividing 1 by 8, we get 0.125. Dividing 36 by 8, we get 4.5. Dividing 4 by 8, we get 0.5. Again, 4 divided by 8 is 0.5. 0 divided by 8 is 0. 16 divided by 8 is 2, and so on. And our chi-squared value for the test statistic will be the sum of all of those values in that last column. Add all of those up, and the sum is 11.25. That is our test statistic. Okay, so the observed values will be given to you, O. The expected values you're going to calculate by n times p for each probability. Subtract each of those values, square them, and divide by the expected value. I'll do another example, but this is how we do our test statistic. Okay, now we had 11.25 for our chi-squared test statistic, and if we are going to compare this to, say, a critical value, we're going to use our chi-squared distribution table that I showed you at the beginning. If you're in my class, you can find that on Canvas. You can also use Excel and chi-dist formula if you would like, or you can, some graphing calculators have this capability too. Okay, so we'll find the critical value using our chi-square distribution chart. So let's take a look at that. Oh, sorry, getting ahead of myself. Before we take a look at that, remember degrees of freedom was on our chart. So the degrees of freedom in the chi-square distribution is the number of categories, not the number of observed weights, the number of categories minus 1. So we had 10 different categories, minus 1 is 9. So our degrees of freedom will be 9. Okay, now we have all we need. So going to our chi-square distribution table, remember our degrees of freedom was 9. Now what we are missing is a significance level, is an alpha, but remember if they don't give it to you, it's supposed to be 0.05. So we'll use the column for chi-squared that has 0.05 significance level. And that set of values would cross the 9 degrees of freedom at 16.919. So that's the critical value. So before I cut to the rest of the problem, if you look at the graph at the top, the 16.919 would be the chi-squared that's labeled at the top of the graph, and the critical region would be everything to the right, the shaded area to the right of that. If our test statistic is bigger than 16.919, that means we're in the critical region and we reject the null hypothesis. But if our test statistic is smaller than 16.919, then we're out of the critical region, so we fail to reject the null hypothesis. So our critical value is 16.919. But our test statistic was only 11.25. So that means that we are not in the critical region. So we would fail to reject the null hypothesis because we're not in the critical region. And what that means is if we fail to reject the null hypothesis, we do not have enough evidence to support the claim that the last digits do not occur with the same frequency. Okay, let's do another example. In baseball, World Series is a best-of-7 competition, which means there can be 4, 5, or 6 games played. The table below includes the number of games played in the past 99 World Series. Also included in the table are the expected proportions of each number of games. Test the claim that the actual number of games played fits the distribution by the probabilities. Okay, so let's look at the first column here. For the games, the World Series where there were only 4 games played, we would expect that to be a relatively low proportion of the total. So the expected proportion, they're giving it to us in fraction form here, is 2/16. We would expect these to be the 2 best teams and probably pretty evenly matched. So having only 4 games played would be a little unlikely. So our expected proportion is the lowest of all of them. Notice that for the 6 games played and 7 games played, our proportions are much higher. We would expect those to be closer series, so they would go longer. So 5/16 is the probability for 6 games and for 7 games. And then in the middle row is the actual World Series contest. So 19 of the 99 World Series that have been played had only 4 games to finish. 21 of the actual World Series contests out of the past 99 had only 5 games to finish. Okay, so let's see how well our data in the middle row fits the expected values. Okay, here we go. For starters, identify the claim. The claim is that the actual number of games played fits the distribution by the given probability, so that the probabilities would all be what we would expect. The probability of 4 games played would be 2/16. The probability of 5 games played would be 4/16. 6 games would be 5/16, and the probability of 7 games played is 5/16. The opposite of that claim is that at least one of those proportions is not equal to the claimed value. Okay, so the null hypothesis would be the claim that we have all of our equal signs, and the alternative hypothesis would be that one of them is different. Okay, let's calculate these. So I filled in the first 2 for you, but I want to show you where these numbers came from. The number of games for number of games, remember, and the observed frequencies, if you forgot what n was, I gave it to you in the problem, but if you add up the observed frequencies, 19 plus 21 plus 22 plus 37, you'll get n. I think it was given in the problem, but n is 99. Now the expected frequencies, let me show you where these numbers came from. N is 99 times P, and if you remember from the previous slide, P for 4 games was 2/16. So 12.375 is what we get for our expected frequency. The expected frequency for the next one, let me show you how I got that. 99 was the N times the probability for 5 games, which was 4/16. So that's where the 24.75 came from. The next one would be 99 times 5/16, which is 30.9375. And 7 games had the same probability, so 99 times 5/16 is also 30.9375. So those are all of our expected values. Okay, so when we work up to our test statistic formula, we want to subtract the 2. So 19 minus 12.375 gives us the 6.625. And 21 minus 24.75 gives us a negative 3.75. And 22 minus 30.9375 gives us negative 8.9375. But remember, I'm not so worried about positives and negatives, because what are we going to do in the next step is square those values. So we square each of those values and then divide them by the E. So for the first row in the last column, 43.8906 will be divided by the 12.375. And we get 3.5467. For the next one, 14.0625 will be divided by 24.75 by its E and get 0.5682. And 79.8789 will be divided by 30.9375 and get 2.5819. And the last one, 36.7539, will be also divided by 30.9375 and get 1.188. Okay, add those all up, and our test statistic is 7.885. Okay, 7.885, let's remember that. The critical value now. Again, it didn't give us an alpha significance level, so we have to go to our table, and we had 4 different possibilities: 4 games, 5 games, 6 games, or 7 games. So our degrees of freedom would be 3. And since it didn't give us a significance level, again, we'll use this 0.05 column for chi-squared. And that means we have a critical value of 7.815. So our critical value is really close to our test statistic. So our critical value was 7.815, but our test statistic was 7.885. Now remember, the test, it's always a right-tailed test, so our test statistic is bigger, slightly bigger than our critical value, which means we're in the critical region. Since it's in the critical region, we reject the null hypothesis. But the null hypothesis was our claim, so there does not appear to be enough evidence to support